Hello everybody and welcome. Thank you for joining me today. In today's video, it's going to be a fun one. We are going to be talking about how to find the area of any regular polygon. So in your math class, you've probably been told that the area of a regular polygon is simply 1/2 times the apothem, little a, times the perimeter, big P. Okay, but where does this formula come from? How can we use it? Let's talk about it. So let me sketch out just a regular polygon for us. So let's do that real quick, and let's see what we get. Now I'm going to do my best to draw this, but maybe we will correct it a little bit after the fact, just to make sure that it's good. Honestly, this looks pretty good, but maybe we can clean it up a tiny bit. Here we'll move it in a little bit. There we go, looking good, looking clean, looking fresh. Damn, it looks like this hexagon just got a new haircut. Look at that. All right, here we have a nice regular hexagon. Might not be perfect still, but let's just take it to be perfect. And let's talk about our formula for finding the area. It's 1/2 times the apothem times the perimeter. And you might be new to what exactly is an apothem. Don't worry, we'll get there. But let's first talk about how we can figure out what the area of this shape is. And in order to find out the area of this shape, we're going to use our center point. Here, let me mark up this beautiful regular hexagon. So we're going to take our center point, and then we are going to connect our center point to each of our vertexes. Okay. We're going to connect it to each of our vertexes. Here, let's make the center point even bigger so that it just looks a little bit cleaner. And now we have a bunch of triangles, and we like triangles. We know the area of a triangle. The area of a triangle is, so the triangle area formula is what? Well, it's 1/2 times our base times our height. Okay, so again, this is a regular polygon. So a regular polygon means that all of our sides are congruent and all of the interior angles are congruent. So we're just going to call our side length S for side length. And we are looking for the height, okay? And the height, the drop down from the center to the side length, this is what is called your apothem, okay? And your apothem not only is a drop down from the center to one of your sides of your polygon, it also bisects your side. Therefore, this half and this half are going to be equal, and also it's a perpendicular bisector, so it's going to form a couple of right angles for us. However, we know that our triangle area is again 1/2 times base times height, so we're going to keep the 1/2. Our base, we defined it to be S. Our height is defined to be the apothem, A. And so this is the area for one of our triangles. However, we're not looking for the area of just one triangle. We want the whole kahuna. We want the whole polygon. And so how many triangles are there? Well, there's 6 triangles. But before we just tap on a 6 at the end and call it a day, we need to convince ourselves that these triangles are congruent to one another, that they all have the same area. So let's do that real quick. This is going to be a pretty lackadaisical proof, but since this is a regular polygon, again, all of the outside edges, all of these side links are congruent with one another. They're all the same. And since we drew a line connecting our center point to each of our vertexes, and because this is a regular polygon, all of these sides are going to be the same. So we constructed a bunch of congruent isosceles triangles when we did this. And we know that by the side, side, side triangle congruence postulate. Okay, so yes, all 6 of these triangles are congruent. Now, instead of just tacking on a 6 here, because this is a hexagon, I want to keep it a little bit more general. Okay, I happen to draw a hexagon, but this formula works for any regular polygon. It could have 7 sides, 10 sides, 12 sides, could have 100 sides. It works for any regular polygon. And the number of triangles that will be constructed from doing this is going to be equal to the number of sides you have. And you can easily see that here because each of the sides of our regular hexagon here is the base for one of these triangles. So the area of our full polygon, I guess I'll call it our polygon area. Our polygon area is going to be equal to 1/2 times the side length times the apothem times the number of sides in our polygon. Okay, and there we have it. Now you may be asking, hey Griffin, this formula you just wrote does not match what my teacher told me up here. What about this? What about the perimeter? Well, think about it for a moment. The perimeter is just equal to the side length times the number of sides in which we have for a regular polygon. And so this formula is equal to 1/2 times the apothem times S times N, which is our perimeter. So these are equivalent formulas. Okay, so this formula is a good one. That's fantastic, but this video is not finished yet. In this video, we're going to be talking more about the apothem. How can we use this formula if the apothem isn't given? What if we're asked to solve for the area of a regular polygon, but all we have is a side length? So let's talk a little bit more about that. Let's see if we can define our apothem just in terms of our side length and the number of sides with our polygon. So let's go ahead and duplicate. Let's duplicate this beautiful regular hexagon. Let's scroll down to a new page. So here we have it. Here we have it. So again, and let's construct those isosceles triangles again, or at least one of them. Let's just focus in on this bottom one here. So here we have some isosceles triangle, and again, we know that the perpendicular dropdown is going to be our apothem. And as each of these side lengths are side length S, we know that since both of these are congruent, both halves of our base are congruent, we know that this bottom base is of length S divided by 2. Okay, now this is where it gets fun. This is where the trigonometry meets the geometry, and we want to put in our apothem in terms of S. And in order to do that, we're going to need to use one of our trigonometric functions. Okay, so let's define this angle to be theta. And so are we going to be using sine, cosine, or tangent? Well, just remember our good friend SOHCAHTOA. And which one are we going to be using? Well, from tangent, we have our opposite side and we have our adjacent side. So we're going to be using tangent. So our trig tells us that the tangent of theta is equal to our side length over 2 over our apothem. Now we're looking to solve for our apothem, so let's multiply both sides by a to get a times the tangent of theta is equal to S over 2, and then let's divide both sides by tangent to have that our apothem is equal to S over 2 over tangent of theta. And then let's go ahead and put our 2 in the denominator with tangent. So we have our apothem is equal to s divided by 2 times the tangent of theta. Okay, so this is handy. This is handy and everything, but what is theta? We need to have a value for theta in order to compute what our apothem is. Okay, so how can we figure out what tangent's value is? Well, let's clean up this picture a little bit. I'm going to erase theta there. We'll add it back in a moment, but let's go ahead and reconstruct our other triangles so that we can think about it a little bit. So here we have 6 congruent isosceles triangles. Again, we know them to be congruent because if we're drawing identical lines from the center to each vertex, all of these lines will be congruent. So we have a bunch of isosceles triangles, and since it's a regular polygon, all of our side links are congruent. So by side, 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 triangle congruence postulate, we know all of these triangles are congruent. And with that, we can use CP/CTC, or congruent parts of congruent triangles are congruent, to tell us that all of these angles here must be equal to one another. Okay? And all of these angles combined add up to what? Well, it's going to add up to 360 degrees, of course. It's a full circle. But we're not interested in our full circle. We're just interested in theta. And theta is what? Well, theta is half the value of one of these triangles. So we're going to take 360 degrees and we're going to divide it by the number of triangles that we have. And like we talked about a minute ago, the number of triangles we have is equal to the number of sides of our regular polygon. So we're going to divide this by n. And that will tell us the angle measure for the top portion of one of our isosceles triangles. However, we're then going to also divide by 2 because we cut our triangle in half with our apothem. So theta is equal to 360 degrees divided by 2n, which of course simplifies to 180 degrees over n for our theta. So we can say, so let's clean this up. Let's clean this up. We can say that our apothem is equal to s divided by 2 times the tangent of 180 degrees over n. And here I'll move down a little bit. There we go. So we have our apothem in terms of our side length and in terms of the number of sides of our polygon. That's fantastic. Now again, remember here, let's clean up our left-hand side as well. We don't need this now that we've solved for A. So this is fantastic, but remember this is a question about the area. And we know that our area of our polygon is equal to 1/2 times our apothem times our perimeter. Again, we know that perimeter is just equal to our side length times the number of sides in which we have. So now let's put this all together. Here I'll even change colors to this nice green. So we know that our area is going to be equal to 1/2 times our apothem times our perimeter, which is just s over n, or s times n rather. And our apothem is this full mumbo jumbo. So it is area or equals 1/2 times s divided by 2 times the tangent of 180 over n times s times n. And let's put it all together in one clean formula. And we have area equals, so the 1/2, this 2 will multiply by the 2 in the denominator to give us a 4 in the denominator, and this s in the numerator will multiply by this s and this n to give us s squared times n divided by 4 times the tangent of 180 degrees over n. And there we have it. So just from if you only have the side length of your polygon, you can calculate the area. And let's just do that for fun really quick. Let's say that, hey, let's say our area or our side length of this hexagon. Now let's do it, let's make it something somewhat simple. Let's say it's 10. Okay, what's the area of this hexagon? Well, we can just plug in 10 for s. Here, let's scroll down, give us some room. We have that our area is equal to 10 squared times 6, because we have 6 sides in our polygon, divided by 4 times the tangent of 180 degrees divided by 6. That's, of course, 30 degrees. And so what is this value? Well, 100 times 6. Well, let's simplify first. We can cancel the 6 and part of the 4 to give us 3 and 2. And then 100, 10 squared is 100. That cancels with the 4 or with the 2 to just be 50. So we have 50 in the numerator and then tangent of 30 degrees in the denominator. I don't know tangent of 30 degrees off the top of my head, but I do know how to figure it out. So how do you figure this out? You construct, we can make a nice 30, 60, 90 right triangle. Okay, so this is what you have to do if you don't know your trig values off the top of your head. So we have a special right triangle where this is some x, this is an x root 3, and this is a 2x. We know the tangent is opposite over adjacent. So we know that tangent of 30 degrees is going to be equal to x over x root 3. Of course, we need to radicalize this, so we'll multiply by our root 3's. Our x's will cancel and we'll have root 3 over 3. So our area, going back to my pink color, our area is equal to 50 divided by root 3 over 3. Root 3 over 3. Dividing by something is the same as multiplying by the reciprocal. So let's just multiply it by the reciprocal and have 50 times 3 over root 3. So this is 150 root 3, or 150 over root 3 rather, 150 over root 3. Again, you can't have a radical in the denominator, so we'll multiply by root 3 again and have 150 root 3 over 3. The 150 and the 3 simplify to just give us 50 square root 3. So the area of this regular hexagon is 50 square root 3, and all we had was the side length being 10. So there you have it. That's how you can solve for area with only the side length. You can use these great formulas. I hope you found this video helpful. If you did, hit that subscribe button, and I'll see you in the next video.